And the first one we're going to talk about is a perfect square. So this is what you need to have written in your notes then. So we're still talking about factoring, and we're going to use like the three methods we know. But in this case, we're going to see some special cases, some things that are going to look like a little bit weird and different. I don't like that lighting. Let's see if we can make that better. Oh, that's way worse. So that's good. Yeah. All right, so for this first example, let's use x squared plus 18x plus 81. Now, this might actually look similar to something you've done before, and it should, because I'm relying on your past knowledge to be able to help you through problems like this, okay? So looking at this, we can think, you know what, it's just kind of a normal factoring thing, right? There's an a term out here, but it's just one, so we don't have to do anything special. One thing that some people like to do is they like to put this into like the rectangle, the area model, or the table. So let me show you what that would look like. If we take a rectangle and we divide it into 4 quadrants like that, remember doing this when we first learned like multiplying polynomials? We ended up getting an x squared somehow, and we ended up getting an 81. And when we combine them, we end up with this here. So what we're missing is this stuff in the middle. And so when we factor this, we already know that we're going to end up with x's to begin with because the a term was 1. So it's the only way you can make x squared is by multiplying the 2 x's together. So you can write it in the parentheses like that, or if you're a more visual learner, maybe you like to put it on the outside of the rectangle. What we're doing is we're deconstructing this polynomial using kind of 2 different ways of looking at it right now. And we know that we want to multiply to make 81, but add to make 18, right? So we're looking at the factors of 81 that add to make 18. Well, wait a minute, isn't that just 9? 9 times 9 makes 81, and it also makes 18. So if I fill in my rectangle right here, it looks like we're going to have 9x in both of those. So this is how they created that polynomial. And they're all positive, so this is plus. So they did x plus 9 times x plus 9. Does that make sense? Any thoughts, questions, wonderings on that? They call it a perfect square because notice the binomial is the same thing. They just multiplied this times itself, right? So there's actually one more step we need to do then. Since it's this times itself, then the actual answer would look like this. We can simplify it a bit more by writing x plus 9 squared. This is going to be your answer to this problem. You see what happened there? It was the x plus 9 times itself. So how can you write that? Well, you can just write that with an exponent here. So this is what all perfect squares look like. They have 3 terms in them. And when you factor them, you end up with a square out here because it's the thing times itself. These are perfect squares. Okay, let's try another one. And if you want, you can use the square or the rectangle I drew. Or if you want, you can always just jump right to the parentheses. There's kind of 2 different ways of thinking about it. So on this one, let's take x squared minus 4x plus 4. So someone help me. What do you want to do first here? What comes to mind first when you're thinking about that, when you're trying to solve it? Any ideas? Yeah. Nice. Yep. And that's kind of the best thing to do is, right, you want someplace to start. So make your parentheses and you know there's two x's. Nice. And now we need to multiply to make 4, but add to make -4. And so something multiplies to make a positive, adds to make a negative, and we have 4s. What comes to mind? I don't know about you, but for me, a 2 comes to mind. Kind of like a 2 times 2 would make 4, right? And if you add them, they make 4. So we just have to see, can we make it positive and negative? Oh, if this was minus, wouldn't that work? They multiply to make -2 multiplies to make +4, but adds to make -4. Hey, that works. But don't forget that last step. And this is where algebra students miss a lot, is you guys get the factoring usually at this point. You can get to your pieces, but you forget to do this. You forget to say, oh, wait a minute, that's the same thing. So we write x minus 2 squared. Because now it's nice and simple. Okay. In the lesson today, like we're doing all these perfect squares, and so you know it's going to happen. But really, in real life and in the problems you're going to be doing, you don't know if it's going to happen. You're going to be going through a normal problem, and all of a sudden you'll be like, wait a minute, that looks a little special. And then you have to remember, oh yeah, I have to write it as squared. Okay. Let's try one more like this. Let's take 4x squared minus 12x plus 9. Ooh, we have an a term out there now. Our a is 4, our b is -12, our c is 9. So that tells us we're going to switch and we're going to do that whole a times c thing, right? So look for the factors of a times c that add to b. But before you do, you always have to ask yourself, is there something you divide out first? Can we divide them all by 2? No. By 3? No. By 4? No. Okay. So we can't divide something out, so we have to then switch to this. So we're looking for the factors of, would that be 36 that add to -12? What can you think of? What are the factors of 36 that would add to -12? You can use calculators, you can use mental math, you can write them all out. You always start with like what, 1 and 36? No, those aren't going to work. Ooh, thanks, Sanvi. -6 and -6. There we go. See, those add a -12. Ooh, look, this is my first idea that this is going to be something special. You see how it's the same number times itself? Okay, so we're going to keep following the rules that we know for this method. Is we have to split this apart. And so what we get is we get 4x squared minus 6x minus 6x plus 9, right? This is like the homework we just corrected. And then we have to treat the beginning and we have to treat the end kind of separate. And almost always, when you divide something out here, you can almost always take an x out. And I already see that that's the case. So I know that I can divide them both by an x. And then I'm thinking, can I divide them by 2? Yeah, maybe something larger. No, I can divide the 4 by 2 and the -6 by 2. So if I divide 4 by 2, I get 2. And I took one of the x's and moved it on the outside, so there's an x in there. And if I divide -6 by 2, I get -3, and I already moved the x to the outside. So that one's factored. Now I look over here. Ooh, I can divide them both. I can divide the 6 and the 9 by 3. Let let me try that. If I take out a 3, then, oh wait, this would be a -2 in here, and I want to be a +2. I don't want the thing inside here to be different. So actually, let me take out a -3. If I divide out a -3, -6 divided by -3 would be +2. Ooh, and there's that x. So this is good. They're matching so far. And then 9 divided by -3 would be -3. Cool. Good. You notice what's going to happen here? Something special is going to happen as we start to finish this. You see it? Okay, let's keep writing out. So we know that 2x minus 3 is one of the binomials. And then the other one, we get it by pulling the pieces from the front here. Ooh, it's the same thing. This is really just 2x minus 3 squared. And our first hint that we were going to get that was up here. When we found that it was -6 and -6, that told us that the thing they multiplied was like the same thing. And sure enough, it was. Down here, we find out this is what they used. Okay, so that's one kind of special case you see. You see these perfect squares, and they look nice and neat, and like it just simplifies so nicely like that. There's another one too. So let's look at the other type that you might run across. And I'm pretty much out of room on the side, so I'm gonna flip my paper over. You don't need to know the name of this, but it's called difference of two squares. One is perfect squares, that's one we just learned. This one's going to be called the difference of two squares. And what that means is like if you were taking the area of two squares and you were subtracting them, you end up with a lot of things like what we're going to see next. And we're going to renumber. We're going to start numbering at 1 again because these are still special cases, but they're not totally, but they're very different than what we just did. So let's say we had this polynomial, x squared minus 225. Notice it's missing that middle term. It's like a really short polynomial. It's missing the b. It's missing the x's. It just has an x squared. But they still created it with two binomials. And what I could do is I could, yeah, I'm going to sketch out that rectangle idea here, that kind of the area model. If they were going to create it, what did they create it with? We know that they multiply something and get x squared, and we know they multiply something and get negative 225. But whatever was in this boxes here, whatever they multiplied here, they canceled out, they went away. So I guess as I factor it, what I'm asking myself is what are the factors of negative 225 that add to make 0? Because there is no b term, b is 0. So there's only one way to make x squared, that's x. And to get something to add to make 0, it means like you're adding a negative and a positive. You're adding like the opposites of each other. And so really there's a shortcut to this. All I have to say is, what's the square root of 225? Or what times itself makes 225? Can you think of it? It's not 12. It's a lot more than 12, right? So calculators, let's get our calculators in with us. We do the square root of 225, we find it's 15. So if we multiply 15 times itself, we make 225. But we need them to add and go away. So we need these to be opposite of each other. I'm going to write my minus like that. So because this would be 15x and this would be minus 15x if we multiply them. So that's how they created this, is they used x plus 15 and x minus 15. That's my answer. So it's almost like the perfect square thing we're looking at, where it's like the thing times itself. The only difference here is it's not the exact same. One's a positive 15 and one's a negative 15 because they cancel out the b term and they go away. Okay, let's try another one and let's see if we can find kind of a shortcut way to do it. We'll call this number 2. So you had x squared minus 64. I really like these because it's so obvious when you have one. There's no b term. So it tells you right away. It actually tells you a couple of things right away. One, it tells you that in your binomials, you're going to have a plus and a minus because they have to cancel out. And we already know these are x's. And so then we just have to ask ourselves, what times itself makes 64? Or like, what's the square root of 64? What times itself makes 64? Yeah, 8. So positive 8 and negative 8. There you go. If you get really good at these, they go really quickly. You're like, oh, that's what I have. So I know it's a plus and a negative, or a plus and a minus. And so I just need to figure out the square root of 64. There you go. Nice. Thank you, Mateo. Yep. Okay, let's do one more. Let's do 16x squared. Ooh, there's that a term that's large. Okay. Minus 81. So because we have that 16 out there, we could totally do the a times c thing and find our b, but in this case our b is 0, but that's going to be way longer. We don't need to do that. This is going to act just like these other ones did. Okay, so I already know that I'm going to have parentheses. We already know that the b has to add to make 0. So we know this has to be a plus and a minus. What else could we fill in? What else do you already know? Yeah. The x. So we know part of it. We know that there's an x in both of them. But we are going to have to deal with the 16 out here too. Right? That makes it a little bit more tricky. Ooh, thank you, Mateo. I see yours too. You say 9 and 9. Right? Now with these, we have to have these two binomials to be almost the same. The only difference, if you look back here, the only difference between each of these was just the plus and the minus. That's the way all of these work. So we need to figure out a way to make 16 by still having these be the same. And the nice thing is the square root of 81 was 9. We can do that again here. What's the square root of 16? 4. So 4x times 4x would give us the 16x squared. And look, this whole thing matches just like it did before. The only difference is now we have a 4 in there. Okay, so that's another kind of difference of two squares that you see. Don't worry. Don't be concerned when you see the 16 and think you have to do a whole bunch of extra work. You don't. You just have to be more careful. You have to make sure that you find the square root of that and the square root of the 81 as you're filling in your terms. I hope that makes sense. The more you apply it, the more you see it, the more it'll stand out to you as you go. Okay, so our purpose today is to be able to solve the difference of two squares and to solve perfect squares. And you either end up with binomials that are pretty much the same, except for the plus and the minus, right? That's what these ones look like. Or you end up with these ones where it's the same binomial times itself. And then you just have to make sure that you write your answer as with that square, with that power of 2 in there, okay? That's actually all of your lesson today. It's pretty short. You ready for homework? And you know what I'll do? I'll just write it on my paper here, tell you what it is. And for those of you at home, I'll turn it on Schoology too.